1. Introduction, Business Reality. Hello. Welcome to a piece dedicated to machine learning on tabular data. We are often swept away by the magic of the latest trends in AI. We see breakthroughs in generative artificial intelligence, large language models, and computer vision. However, if we look at real production systems in banking, insurance, e-commerce, or logistics, the picture is very different. Billions of parameters do not rule there. Tables do. Most of the business value in today's machine learning is generated by structured data, rows and columns. This is where credit decisions are made, financial fraud is detected, and supply chains are optimized. In this video, we will put marketing hype aside and focus on pragmatism. I will explain why classical approaches still outperform deep neural networks and how to navigate the modern tooling ecosystem wisely, from XGBOOST to TabPFN. Our goal is production effectiveness and stability, not architectural novelty. 2. What is tabular data and why is it hard? Let's start with the basics. Tabular data consists of datasets where each row represents a single entity and each column represents a feature. We also have clearly defined labels. It may seem simple, but from a mathematical modeling perspective, this type of data is extremely demanding. In images, we have strong spatial correlations. Neighboring pixels form edges and shapes. In text, we have sequential structure. Each word depends on the previous ones. Models like CNNs or transformers exploit these specific properties. They possess what is called an inductive bias, an inherent assumption about the structure of the data. Tabular data lacks this convenience. The order of columns is arbitrary. Changing their position does not change the information, but it drastically changes how a model has to process it. Additionally, tabular data is heterogeneous. In a single table, we have floating point numbers, categories, dates, and Boolean values. Data is often missing, and relationships between features are nonlinear and discontinuous. This makes finding universal patterns much harder than in continuous signals such as audio or images. 3. Classical models that still win. Despite the passage of time, a few proven solutions still dominate the world of tabular data. At the beginning, we have linear and logistic regression. They are simple, interpretable, and make excellent baselines, but they rarely offer top accuracy for complex data. The real breakthrough came with random forests. They demonstrated the power of ensembles of weak learners, in this case, decision trees. Today's industrial standard, however, is gradient boosting. Models such as XGBoost, LightGBM, and CatBoost are the workhorses of modern machine learning. Why do they win? First, they handle nonlinearity extremely well without complicated pre-processing. Second, they automatically detect feature interactions. Third, they natively support missing values and categorical data. Most importantly, they perform exceptionally well on small and medium-sized datasets where deep learning usually fails. If you are working on a model and did not start with LightGBM or XGBoost, you are probably wasting both your time and your company's money. 4. Why do neural networks fail on tables? A common question arises: if neural networks have revolutionized the world, why haven't they done the same for Excel? The classic multi-layer perceptron, MLP, struggles significantly with tabular data. The main reason is the lack of the inductive bias mentioned earlier. Neural networks are smooth function approximators. Tabular data often requires step functions and sharp thresholds. For example, if age is above 18, then do X. Decision trees handle this naturally. Neural networks try to smooth these transitions, which often leads to severe overfitting. Moreover, architectures like CNNs search for local patterns. In a table, locality does not exist. The first column may be strongly related to the 100th column. Transformers, on the other hand, are very sensitive to data quality and require massive datasets to learn relationships that trees can capture in just a few iterations. In practical engineering work, the cost of preparing data for neural networks, normalization, embeddings, missing value handling, is disproportionate to the accuracy gains, which are often negative. 5. The new wave, foundation models, and AutoML. That said, recent years have brought some innovations worth knowing about. They are not standards yet, but they are pushing the boundaries. One interesting example is TabPFN, a prior data-fitted network. Simply put, it is a transformer trained on millions of synthetic datasets. During inference, it is not trained in the classical sense. It passes your training set through its weights and immediately produces predictions for new data. It works extremely fast on small tables and often beats XGBoost without any tuning. There is also TabSTAR, which applies attention mechanisms directly to features, allowing the model to understand which columns are important in a given context. A completely different approach is AutoGluon. This is not a single model, but a powerful AutoML engine. Instead of searching for one perfect architecture, AutoGluon builds multi-layered ensembles, combining trees, neural networks, and k-nearest neighbors into a single structure. For an engineer, this is often the best choice. You feed in the data, and the system automatically optimizes the model stack for a specific business objective. Demo moment. Here, you could show that AutoGluon achieves better results in a few lines of code than a manually tuned XGBoost. 6. Google's approach to tabular data. It is also worth looking at how Google approaches this problem. Their philosophy is highly pragmatic. Google sells infrastructure and time, not magic black boxes. In Vertex AI AutoML Tables, you won't find exotic neural networks straight from research papers. Under the hood, Google relies on proven solutions, advanced feature engineering, and powerful tree-based ensembles. An interesting project is TensorFlow Decision Forests. Google created a library that allows you to use random forests and gradient boosting directly within the TensorFlow ecosystem. This is a clear signal. Even the creators of the most popular neural network framework admit that trees are indispensable for tabular data. There is also BigQuery ML, which allows you to train models directly inside the database using SQL. This approach prioritizes deployment speed over theoretical purity. Compared to TabPFN, Google focuses on scale and enterprise stability, while foundation models are still mostly suited for smaller datasets and fast experimentation. 7. A practical decision guide. So, how should you make a decision in a real project? I've prepared a simple decision matrix. If you have a small dataset, up to 1,000 rows, start with TabPFN or a simple random forest. They are robust to noise and require little tuning. In standard medium-scale production projects, your first choice should be light GBM or XGBoost. They are fast, predictable, and easy to monitor. If you work in a large organization where time to delivery matters more than what's under the hood, use AutoGluon or Vertex AI. They remove the burden of hyperparameter optimization. If full interpretability is critical, for example, in medicine or law, stick with logistic regression or EBM, explainable boosting machines. Remember, business context always beats model novelty. Choose the simplest tool that solves the problem with the required level of accuracy. 8. Summary and conclusions. Let's summarize the key takeaways. Tabular data is the heart of business machine learning, but it follows its own rules. Decision trees and their boosted variants still dominate, and there is no indication that this will change anytime soon. Neural networks are powerful, but in the world of tables, they are often too costly and difficult to maintain. Modern tools like TabPFN and AutoGluon shorten engineering time, but they do not absolve us from thinking about data quality and proper problem formulation. My final advice: be pragmatic. Don't look for problems for the latest architectures. Look for the simplest architectures for your problems. Real engineering is about delivering working solutions, not chasing hype. Thank you for your attention. If you have questions about specific deployments, the comments section is open. See you in the next piece.